Are we recording? I think so. Yeah, okay. Let's do this. So first thing I wanted to do today is I wanted to talk about something that I referred to in the last video lecture, which are laws of probability. So let's start with the first law. For any event A, zero is less than or equal to the probability of A is less than or equal to 1. So note this actually, so this is the first thing, and note I have introduced notation, the shorthand for the probability of A is P of A, right? That's basically how you would read that. If you saw P of A, you would read, oh, the probability of the event A. And note also that this is unremarkable. It's really just such a waste of a law. And the reason it's such a waste of the law is it's just a consequence of the definition of a probability. Recall before I said that it is the long-term proportion of times. If I were to observe the outcome an infinite amount of times, it is the long-term proportion that I get a success, right? If I flip a coin 1 billion times, I'm expecting it to become 0.05% of the 0.05 proportion of the times heads. So a probability is defined as a proportion, and proportions are always between 0 and 1. It's the proportion, it's the how much of the total, right? So this happens kind of trivially because a probability is a proportion. Law 2 was the probability of the sample space is equal to 1, where S is the sample space. And note, this is also kind of unremarkable. So if a probability is always between 0 and 1, the probability of something happening, or the probability of every single outcome added together, has to be equal to 1, because that's just the total. What's the if we're asking what proportion of times do I get heads or tails from flipping a coin, well, every time if I flip a coin, I'm going to get either heads or tails. So of course the probability needs to be 1. So I would say this is also all unremarkable. Law 3, we talked a little bit about disjoint. So if events A and B are disjoint, let me make sure I get this right. Okay. Then probability of A or B is equal to the probability of A plus the probability of B. And this one is we're going to talk more on this law on the video lecture, which again is kind of late, my bad. The fourth law is the probability of A complement is equal to 1 minus the probability of A, where, as I just said, A to the C, that notation is the complement of A. And actually, I wanted to talk about this one in the context of one of our homework problems. So on our last homework, I believe, oh, which one was it? So we had, yeah, someone was taking a test. So student took a 5-question test. And we wanted to know what is the probability of event A, which was she got at least at least one question correct. So you could have done this in one of two ways. You could have said, well, the probability of A is equal to the probability that she got one, let's say, only one right, plus the probability she got only two right, plus, 3 plus 4 plus 5, right? And this would have given you the right answer, but note it's a little cumbersome. You have to not calculate one probability, you actually have to calculate 5 probabilities. However, thinking about the fourth law, I'm going to make a claim to all of you. And that is that AC is equal to, she got no questions correct. Right? Do you see how these are complements of one another? Either if A happens, if AC happens, A does not happen. And similarly, if A happens, A complement does not happen, right? And further, one of the two of these events must happen. She either gets one or more right, or she gets none right. There's only one of these two options. So we call these complements. And since they are complements, you could instead find the probability of AC, which is just the probability that she got 0 correct, which was an easier probability to calculate. And then you could have used law 4, which was say, well, the probability of A is just equal to 1 minus this probability. Okay? So these laws, they're good ways to think about probabilities, and they can kind of make these calculations that we do on homework a little bit easier if you think about the rules that they introduce. How do we feel about this? Is this good? All right. So that's what I wanted to say about that. Let's go on to the next topic, which is independence. And I have a definition. Events A and B are independent if knowing that one occurs does not change the probability that the other occurs. So that is the definition, and there's an alternative definition. A and B are independent when the probability of A and B happening, the probability of both of the events happening, is equal to the probability of A times the probability of B. Okay? So we have a new definition. We should, whenever you're presented with a new definition, think about it, say it in a number of different ways, and then look at some examples of it. So we're going to move on to examples of it. But first, I want to make one little note, is there's a shorthand for independence. And that is A is independent of B. You can equally write this as sort of this notation. A is independent of B, this little sort of upside down double-legged T. I'm going to try to avoid using this notation because I think I want to make it as clear as possible. And this can be a difficult concept, and I think it's easier for people's understanding if I just write out what I mean every time. But I wanted to bring this up because you may see this in the future just even outside of this class, people kind of using that shorthand. Okay? So let's talk about examples. Roll a fair die twice. Let event A equal get a 6 on roll 1, and let event B equal get a 6 on roll 2. And I'm going to tell you that these events are independent. Right? No matter what I get on my first roll, 1, 2, 3, 4, 5, or 6, it has no effect on the outcome of the second roll. And whatever I get on the second roll, 1, 2, 3, 4, 5, or 6, has no effect on what I got for the first roll. These events are independent because no matter what I get on one of them, the probability distribution of the other shouldn't change. I should still get each with 1/6 probability. So in this case, since I have independence, if I want to know the probability of A and B, which is the probability that I get 6 on both rolls, which is equal, by the definition of independence, to the product of these two probabilities. And since getting a 6 on roll 1 is a 1/6 chance, and getting a 6 on roll 2 is a 1/6 chance, the probability of A and B is just 1/36. Okay, so this is, if you have independence, probability calculations like this can become pretty simple. Let's do something we haven't done in a little while. Let's do some polls. So this is our idea of probability. Let's see if we can play with some new ideas. All right, can we see it? Yeah, okay. Are the following two events independent? A, it rains in at least 3 of the 50 states tomorrow. Or B, I get 1, 2, or 3 upon rolling a fair die. Yes, no, or not enough information. Okay, I'm gonna end the poll. And can somebody tell me what we got?
92% yes, 0% no, and 8% not enough information.
Ah, very nice. So, sorry, was that a question? Or is that just also some, okay. Yes, the 98, you said 80, 98, 97% of you were correct. These are indeed independent events. I guess maybe the 3% of you who are thinking not enough information might be making this sort of like, ooh, butterfly effect. Maybe the flip of the coin today does actually have some effect on whether or not it rains in 3 states. I will say, sure, but these events certainly are independent in any practical or theoretical sense. Me rolling a die today will not actually affect, and whether or not that die was 1, 2, or 3 versus 4, 5, or 6 is not going to affect the weather tomorrow. These are very safely independent events. Okay, let's try another one. This one's a little trickier. So we can see it. Say we have 5 people labeled 1, 2, 3, 4, and 5. Take a simple random sample of size 2. Let A be the event that the first person has chosen, and let B be the event that the second person has chosen. Are these events independent? All right, about 5 more seconds. Can somebody tell me how he did?
12% said yes, 77% said no, and another 12% said not enough information.
Very nice. So actually the no's are going to take the cake on this one, but it's not immediately apparent why that is. If I pick 2 people, does the fact that I picked one affect the fact that I picked the other? The answer is no, and you can certainly try to reason, just like how we did with the weather and the rolling of the die example, you can kind of reason as to why they're not independent. Or you can use the definition to prove that they're not independent. And I'm going to show us how to do that. So recall I said that an alternate definition is that this is true. This sort of probability of A and B is equal to the probability of A times the probability of B. Well, let's look at our sample space. What are the different possible ways that I could pick a sample of size 2? I could pick 1, 2. I could pick 1, 3, 1, 4, 1, 5. I could pick 2, 3, 2, 4, 2, 5. Pick 3, 4, 3, 5. I could pick 4, 5. So what is the probability? This is my sample space. What is the probability that I get A and B? That is, I pick the first person and I pick the second person. Well, that is just this one right here. And how many are there in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of A and B is 1/10. On the flip side, the probability of A, so what's the probability that the first person is chosen? That would be, let's see, it's chosen here, 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 and here are the outcomes where the first person is chosen. So what is that, 4 out of 10? Right? That's the probability of B, that 2 is chosen. I think 2 is chosen here, 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 and here. So again, that would appear to be 4 out of 10. Therefore, the probability of A times the probability of B is equal to 4 out of 10 times 4 out of 10, which is 16 out of 100, or 0.16, right? And notice something. Probability of A and B was equal to this, 0.1, and probability of A times probability of B was equal to this, 0.16. They are not equal. Hence, they are not independent. All right, so this was actually just a consequence of the definition of independence. We checked to see if these two quantities were equal, and they weren't, not independent. So you could have also just looked at this and kind of reasoned as to why they wouldn't be independent, but ultimately if it's sort of like, maybe so, maybe not, check the math, see if it works, okay? Okay. So we have one more poll, and this one is the trickiest one. I'm interested to see what we think. All right, from a very large population, we can see it, right? From a very large population in which 40% identify themselves as Democrats, take a simple random sample of size 5. What is the probability that they're all Democrats? I.e., event A is first drawn as a Democrat, event B second drawn as a Democrat, and so on for C, D, and E. So are A, B, C, A through E independent? Not independent. That 31 should say approximately independent, or is there not enough information? So I'm gonna give us like 10 more seconds. Okay. Can someone read me the results?
8%. Oh, sorry. 8% say these events are independent. 50% say they're not independent. 38% say they're approximately independent, and 4% say there's not enough information.
Very nice. So actually, in this case, the 38% are getting the cake. And that is because when you take, and I'm going to write this as a rule, and then I'm going to try to loosely justify it. So rule, if the simple random sample you take represents approximately less than 10% of the total population, you may say they are approximately independent. All right. And the way I want to kind of motivate this is note, okay, so it said 40% of the population. So say we're dealing, say the population was 40 million people. So what's the probability that my first person picked was a Democrat? That would be, it would be 10, right? 40%? Oh, I should do this differently. Let's do 10 million people. Let's do 1 million people. So 1 million people, ton of people, right? So 40% is 400,000 out of 1 million, right? So if I were to pick a simple random sample of 1 million people, if I get anyone in that 400,000, that's going to be a Democrat, and that is approximately 0.4, right? Because I'm saying 40% of the time I'm going to expect to get a Democrat with this huge population. Now say you pick a Democrat on your first one. What's the probability that the next person is a Democrat? Person 2. Well, it's actually going to be what? 399,999. Oh, I should do this on a new page. 399,999 out of 999,999, right? Because I've already taken 1% of the population. There's one less than 1 million people in the population now, and there's one less Democrat. And actually, if you do this, this is still approximately 40%. So yes, it changed ever so slightly, but that ever so slight change with huge populations is negligible. And because of that, whenever we take a simple random sample of a huge population, we can assume that these observations are independent because the probability of us picking a Democrat every single time remains 40%. So that's the idea. If that doesn't quite make sense to you, that's okay. Just remember this rule that you can get independence from doing a sample. Every single draw is independent in this, as what is the case in our poll right here, when you're dealing with a huge population and you're taking a relatively small sample of it. Okay? But this is the idea. Okay. Let's move to another example. Suppose You are in a class of 15 students, including yourself. And your professor chooses students at random to answer questions. Suppose further she never picks the same student twice. And she has 3 questions. To ask. What is the probability that you are not picked? So, there are 2 ways of thinking about solving this problem, and one way allows you to use independence, and one way does not. So let's look at the first way. The probability of not picked, we can say this is the probability of not picked for question 1 and not picked for question 2. And not picked for question 3. But something to note here is that these 3 events are not independent. Remember, I said independence is when the outcome of one event doesn't affect the outcome of any of the others. Note here that if this first event, I'm going to call this A, if A is not true, then the other events are automatically true. Right? So it's a double negative. So if A is not true, if I was not picked for question 1, that means if I was picked for question 1, right? So if A is not true, which means if I was picked for question 1, then the other events are automatically true. If I'm picked for the first question, I'm not going to be picked for the second 2 because we said my professor never picks on the same student twice, right? And because these events interact with each other in this way, they are not independent events. So I cannot just say the probability of this times the probability of this times the probability of this, right? What I would actually have to do I'd have to write out the sample space. I'd have to think about how many different possibilities there would be, right? So if the students are labeled 1 through 15 and maybe I'm student 14, right? Maybe she picks student 1, then student 13, then student 2. That would be an outcome that could happen in the situation. She could pick 2, then 3, then 4. She could pick me, then I'm 14. She could pick me, then 15, then 1, and so on and so forth. And in fact, if we wanted to talk about what is the size of the sample space, I would say, well, she can pick any of one of 15 students for the first question, And she could pick any one of 14 questions for the second question, and she could pick any one of 13 students for the third question. So actually it would be this product, which actually, I wonder what that is. 15 times 13, which would be this many different options. So it's a huge sample space. And what you would do is you would just think about how many of these don't include me. And then take the proportion. And that's one of the ways that you would solve this problem, but it is not able to use independence, right? I'm going to show you the other way to solve it, which does use independence. And that is to rephrase it. So I'm going to claim that not being picked, the probability of not being picked, is equal to the probability that not picked for question 1 and probability that probability that I'm not picked for question 1 and that I'm not picked for question 2, given not picked for 1. And I'm not picked for 3, given not picked for the others. So these events actually are independent. So if you rephrase it in this way, these events are independent, and you can actually write them as the product of the probability of this event times probability of this event times probability of this event. And what that would look like is me not being picked for question 1. That is, she picks one of the 14 other students out of the 15. And given that I wasn't picked for the first one, the probability that I'm not picked for the second one is that she picks one of the other 13 questions out of the remaining 14 of us who haven't yet to be picked. And the probability that I'm not picked for the third, given I wasn't picked for the others, is that she picks one of the other 12 students out of the 13 possible students who have yet to answer a question. And this is the answer. This is another answer. And actually, no matter if you had done it the first way or the second way, you would have come to the same answer. But the thing about this one is we actually use independence. And notice something kind of cool, that the sample space changes. As we move forward with this one. So the reason I bring this up, and I'll take questions in a second if there are any. The reason I bring this up is because I think a lot of you have probability experience from previous classes, whether that be from high school or from other college classes. And I've seen a lot of you use these sort of product tricks. And these product tricks are valid, and if you know how to do them properly, you're welcome to use them when you solve probability questions. But know that you only really product probabilities together when you have independence. And you need to be careful that you do actually have it, because we didn't have it if we had just worked with here from these 3 events. But if we thought about it in the right way, then we do have it. Okay? Are there any questions?
Earlier you said 5 or 15 times 14 times 13 for the size of the sample. How did you get that?
Oh,
How did you know
well, it's sort of a counting way of thinking. If you think about it, she has 15 different options of who to pick for the first question, right?
Mm-hmm.
And once she has picked that person, she has 14 different options of who to pick for the second question. And when she has picked 2 people, she has 13 options of who to pick for the third one. So actually, if you wrote it out, and this might be difficult to think about. It looks like one, so say instead, it's hard to write for 15, but say instead there were only 5 students. 1, 2, 3, 4, 5. And I wanted to know the different number of ways she could pick like she could pick ask 3 questions to 5 students in this way. You could actually think about it this way. So she could pick the first person for the first question, then the second person, then if she picks the first person, the next person she picks has to be one of these people, right? So there are 4 options. If she picks the second person first, then again, there are 4 different things she can pick, anyone but the second person, right? And that is true for every single one of these, for 1, 2, 3, 4, and 5. Once she
Yeah, I think I got what you meant now.
yeah, you get what I mean? And then once she's
Mhm.
picked 2 and then 1, if I go from here to here, then she can only pick 3 people, right? So it's a matter of like how many different paths through this. And the number of paths using this sort of logic is what I got right here. It's sort of a classic counting problem. And you can think about it with this sort of web that I'm drawing right here. Or you can just kind of think about, how many different ways can she pick 3 people from a class of 15? And that's something you kind of have to reason through, and you kind of just have to do these problems a lot to get an intuition about what that is.
Okay, thank you.
Of course. Any other questions? Okay. That's that one. All right. So that was independence. That is certainly going to come back. But let's talk next about random variables. So recall our first step for defining a probability distribution. Which was describe a phenomenon. So I'm going to introduce to you something called a random variable, which is one means by which we do this. It is sort of an introduction to an explicit notation. So maybe I should just give you the definition instead of trying to give you big picture ideas. Might be better to do definition and examples with this one. So definition. Variable or random process with a numerical outcome is called a random variable. Which we denote as X. So many times in this class already, in fact, maybe I'll write this. Many times in this class already, we've been describing oh goodness. Sorry about that. A random phenomenon. Excuse me. When we've been describing a random phenomenon, we've really been describing a random variable. So let me give you an example of what I mean by it. It's really something we've already tackled, but there is, now we're kind of talking about the explicit notation, like how we think about a random variable in terms of like mathematic and algebraic notations. So let's do some examples. Roll a 6-sided die. And call its outcome X. So previously, we talked about rolling a 6-sided die and getting a number 1 through 6. And we said, oh, you roll a die, say you get 6, right? But now what I'm saying is let X be the outcome of that die roll. Because I don't know what the outcome of the die roll is. It's a random quantity. We haven't observed it yet. And if I want to deal with it mathematically, I need to be able to just describe what the outcome of that die is. So since we don't know it yet, since we haven't rolled the die yet, or since because that could be any number of things, 1, 2, 3, 4, 5, or 6, we instead just put X. Let X be the outcome of the roll of a die. That's the idea. Another example is to randomly choose any number between 1 and 10. Right? Choose any number between 1 and 10. Let that number be X is the idea. Oh, in fact, excuse me. Any number X between 1 and 10. Right? So these are random phenomenons. These are not new to us. We have talked about them. But now I'm saying that, like, since we don't know the outcomes, since there are a number of outcomes that all happen with different probability, if I want to talk about the outcome of a random process, I do so by using this variable, a random variable. Or let X be a test score drawn randomly from a population of scores with a known distribution. Normal mu sigma. Okay? So I could also say, let X be the value of the random draw from this normal distribution, right? We remember our normal curve. X can be any single value from that normal distribution. Just say I randomly chose a test score, and whatever that test score is, I'm going to call it X, but X could be a number of different things. So I can't just write a number because a number is just a number. It's not a great way of describing a random process. So hopefully, if this isn't intuitive to you, it'll become more intuitive as we use it. But this is very much the vernacular when talking about a random process. You define X and you say, hey, X can be any number of things. Okay. In fact, here, let me write this, it might help as well. When we think about random variables, we don't ask what they equal, but rather what are the different values. Oh, dang, I keep pressing that page move button. What are the different, where was I? What are the different values it could be? And with what probability will it be them? Okay. So that's a random variable. I'm gonna talk next about the expected value of a random variable, and hopefully there's an example in this explanation that will, if this doesn't make sense to you yet, will make a little bit more sense. But that's what a random variable is. Any questions? Consider the following probability distribution. Right, so what is a probability distribution? It's the different outcomes we could see and the probability of observing those outcomes. And I'm gonna say something kind of cool is that, so this is, okay, maybe I should describe it first. This table shows the possible revenues the bookstore may get from any given student. And the probability of each outcome. So what I'm going to say is X is the revenue for a random student. From a random student, I guess. So let's see. What do we have here? X here, so X is equal to 0. The revenue we get from a student, the random variable X, it's going to be equal to 0 20% of the time with 0.2 probability. 0.2 out of 10 over the long term, right? X is going to be equal to 137, which is a random student. The value of revenue we get from that student will be 137, approximately 55% of the time, or 55 out of 100 in the long term. And X will be 170. The value of revenue we get from a random student will be 170, about a quarter of the time, right? So this is all of the different values our random variable can take and the probability of each of these values happening. These aren't really new ideas, but it's a slight reframing with this new thing that I'm calling X. So this is X, and this is the probability distribution of X. Let's talk about, I have a question. What is the average revenue per student? Another way of asking this is, over the long term, how much can the bookstore expect to earn for each student? What is the average value of this random variable? And the way that you do that, I'm actually just going to show you it first, and then I'm going to give you the formula. Is you take each of the values, so I'm going to get $0, and you times it by the probability of getting $0. So let's say I get $0 times the probability that my random variable X is equal to $0. Plus, what was the other one? $137 times the probability that my random variable x is equal to 137, right? Times the probability that I get that much revenue from a student, plus $170 times the probability that my random variable is equal to 170. So if I times this all out, this is going to be equal to $0 times the probability of getting $0, which is 0.2, plus $137 times the probability of getting that, which is 0.55, plus $170 times the probability of getting that, which is 0.25. In the end, I get 117.85. So that is the average value. We in fact call it the expected value. And this is, as you might imagine, of major, this is a very important calculation for people who work in industry, right? I know how much I've gotten for every single person that comes into my store. How much can I expect to get for every additional person that comes into my store? And that is specifically, it comes into my store. And that is specifically this calculation. Over the long term, if more and more people come, I can expect to get about this much for every person that comes. Some people I'll get more, some people I'll get less, but it'll average out to this. So yeah, this, if anything, is one of the more, I have to say, since I've taken introductory stats a long time ago, this is probably the calculation for my introductory stats class that I've used the most since. This is definitely something that comes up a lot. Expected value of a random variable. So I'm going to do this formally now. And that is let x be a random variable. And let little x1, little x2 to little xk be the possible outcomes. Then the expected value, and this is the shorthand for expected value, just e of x, the expected value of the random variable x is equal to, oops, here's that summation notation we've seen before, the sum from 1 to k of xi times the probability that a random variable x is equal to xi. And this is actually the exact calculation that I just did in that example. You take the value of the random variable times the probability of getting that value, and you add up all the different possibilities. Note, we often denote expected value of x as mu. Okay? So just like we had an expression for like the average of an expected variable, we also have an expression for the variance, how varied the different values the random variable can take are. So that was expected value. Let's talk about variance. Just like how we calculated the expected value slash average of a random variable. We calculate its variance. Like so. Variance of x, which we actually denote as something we've seen before, sigma squared, is equal to x1 minus e of x squared times the probability of x equaling x1 plus the probability of x2 minus e of x squared times the probability of x equals x2 plus dot 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 plus xk minus e of x squared times the probability of x equals xk. As you might imagine, this is easier to write in summation notation, so there's that summation again. I equals 1 to k of xi times the probability of x equals xi. Oh my goodness, that's expected value. Wow, I've been doing lectures for too much today. So x minus e of x squared times the probability of x minus xi. Okay, and that's the formula for variance. So this measures the variability of a random variable. And just like with our normal curve, larger sigma means a wider distribution of values. So you're going to practice this on homework. I'm going to make a brief warning. Don't round as you go. With the homework problem on variance. And you'll see what I mean when you take a look at the homework, but basically I would suggest opening an Excel sheet and putting the values that it wants in this table from you, and use all of the digits of the values on the table, and don't round those values as you go, because you'll get sort of a cascading error, and it's tripped up people in previous semesters on this particular problem. So do please don't round as you go. You'll run into problems. So I have one final thing I'm going to show you today, and then I'm going to release you for your quiz. Where did it go? Ah, there it is. So recall on this example, we have a random variable. So in this example, with the bookstore, our random variable x took on discrete values. So x could only be equal to 0, 137, or 170, nothing else. And it took on these values with these probabilities. A random variable, as I think I've mentioned in previous examples, can take on continuous values. Like when x is distributed normally. Normal mu sigma. And what that looks like, right? So this is a normal. We have mu at the center, around at the inflection points. We have one standard deviation above and 1 standard deviation below, right? And the idea here is that the random variable x, like also x, can take on many different values, basically every single value on the x-axis right here. And the distribution expresses how often it takes each of these values. So x is more likely to take values in the center and less likely to take values in the edge. This is very much something that we've done before, but now I'm just telling you that when a random variable takes a continuous value, we actually use these density curves to express it, which I think might have been the topic of my most recent video lecture. And I want to mention, in this case, whenever you're working in continuous distributions, this expected value thing is, for normal, is just the mean, right? The center of the distribution. The expected value of this continuous random variable is mu. Variance of x is sigma squared. And of course, as a consequence, standard deviation of x is sigma. Okay? So I think this is where I'm going to stop and open up for your quiz.